All right, folks, this is a video on double displacement reactions. Remember, double displacement reactions usually take place when you have two aqueous solutions with ionic compounds, and those aqueous solutions swap the cation and anion, resulting in two new products. And so over here, we're going to do an example where we have lead nitrate as one of our substances. The formula for lead nitrate is PbNO3, 2. And then the other substance we're working with is potassium iodide with a substance of, or a formula of Ki. Now, the first thing I like to do, and this step isn't mandatory, but the first thing I like to do is draw out my particle diagrams for each substance on its own. And so right away, I know that NO3 is a polyatomic ion that you read about in Async Task 14. So I know that that moves together, and I've memorized the charge of that. I know that that charge is -1. And the fact that there are two of them means that the total charge of NO3 is -2. And the fact that this Pb just has one Pb right there means that the total charge of Pb has to cancel out the charge of both of my NO3s. And so that must mean that my Pb has a charge of +2. That's how I would figure this out. And for my potassium, I'm going to do the same thing. I'm going to draw my individual beakers. Potassium has a charge of +1. Iodine has a charge of -1. And so now I've gone ahead and really isolated my beakers, and I know the particle diagrams that are being represented here. One of the things that you're asked to do is to find the net ionic equation, all right? And you're asked to find a net ionic equation. And in addition, you're also asked to find a molecular equation for when these two substances react. And so what I like to do is identify the cation, in this case is Pb +2, and then the anion here is NO3 minus, and the cation over here is K plus, and the anion is I minus. And so remember, we do a switch. So right now my lead is with my nitrate. On the product side, my lead is going to be with my iodine. And so right away, the first thing that I do is, in order to find my molecular equation, I'm going to go ahead and write out my reactants. I already know that. PbNO3, 2 plus potassium iodide. And now the question becomes, what goes on the right side of the arrow? And the reason I like to write out my cations and my anions like this is because I know that my cation from one substance is going to bond with the anion from the other. And then my anion from the same substance is going to bond with the opposite cation to form both of my products. And so if I have lead as Pb +2 and my anion is iodine, we can use the crisscross rule to come up with PbI2. And so that becomes one of my products. I'm going to go ahead and erase that. And then I work with the other one. So I have K plus and NO3 minus. I do the same crisscross rule, where these are ones. The ones come down. And this just ends up being KNO3. And since there's only one KNO3, I don't have to put NO3, I don't have to put parentheses around it. Now it's important that you remember the polyatomic moves together, right? That's something that you should have learned in Async Task 14. And so now I have my molecular equation, this thing that we just came up with, is called a molecular equation. However, it's not balanced right now. And so I notice that I have two NO3s over here. And so I'm going to pop a 2 over here. I notice that I have two iodines over here, and so I'm going to put a 2 over here. It's really important when you balance that you only touch the coefficients out here. You don't touch these subscripts. You only touch the coefficients. So great, we figured out our molecular equation. Your next step is going to be to break it down to a net ionic equation. And in order to do that, we need to follow our rules and figure out which one of our products is actually a solid. Well, our rules say that any compound with a potassium, sodium, ammonium, and nitrate will be soluble. And so I see a potassium and a nitrate here. They will be soluble, and so I put an AQ over here saying that they will be soluble. We know our reactants are aqueous because they're solutions, which means that this lead iodide doesn't follow our rule, so that's going to be the solid. Now we can start coming up with our net ionic equation. And the way I do that is to break all of these ionic compounds down into their particular components. And the reason that now this step becomes pretty easy is because we've already done that in our beakers up top, right? And we just got to pay attention to one thing. And so Pb and NO3 is going to convert to Pb2 plus I have 2 NO3 minus ions. This 2 comes right over here. Plus, now I have Ki, but I have 2 of them, so that's going to give me 2 potassiums plus 2 iodides. And I'm going to draw my arrow. The PbI2 is a solid, so that stays together. It does not dissociate. Oops. And then I go ahead and do the same thing with my KNO3. So I have 2 potassiums and 2 NO3 minuses. And what you'll realize is you see some things that are similar on both sides of the arrow. So I see 2 K pluses, I see 2 K pluses. I see 2 NO3s, I see 2 NO3s here. And what we can do is cross those out. These things that we crossed out are called spectator ions. Spectator ions don't participate in the reaction. They just watch the reaction happen. And so what I'm left with is this. And this right over here is my net ionic equation. And so you may ask, well, how do I draw a particle diagram for this? Because I know that's the one thing that you all wonder about all the time. And the answer is, if I draw my beaker, what this tells me is that PbI2 is my solid. And so we're just going to draw like a little hump here. And we're going to call this PbI2 solid. That's how we represent solids. And then what this tells me is I have Pb2 plus and iodine that are in my solid, or that combine to form my solid. And what I can't forget is my spectator ions. And so I have 2 NO3s and 2 Ks that are on both sides. And that would be my particle diagram for this reaction of aqueous solutions. All right, and so in this case, we would be done, and then you could move on to the next problem. All right, some things to remember is that it always helps me to start with these individual diagrams so I know what I'm talking about. It always helps me to identify my cation and my anions, and then actually draw this switch and then do the crisscross rule slowly so I know what products I am forming. As long as you remember the rule of what stays solid and what does not, then you should be okay. And then as long as you can watch your subscripts here as they turn into coefficients, then you should be quite all right. Okay, hopefully that was helpful.